Have you ever looked into a car's side mirror or thought about how a giant telescope works and wondered, how does a simple, curved piece of glass do all that? Well, today we're going to crack that exact code. We're going to build a physicist's toolkit, piece by piece, so you can understand exactly how spherical mirrors work.
So, here's our game plan. We're going to start with the absolute basics, the parts of a mirror and their rules. Then, we'll get our hands on the instruction manual, something called the Cartesian sign convention. From there, we'll find a key relationship, build up to the super powerful mirror equation, and finally, we'll put our brand new toolkit to the test and solve a problem from start to finish. Let's dive in.
All right, first things first. Before we can do any cool calculations, we need to know what we're even working with. Let's get the basic tools for our kit and define the fundamental parts of any spherical mirror.
At the heart of it all, there are really two main flavors of spherical mirrors. Over on the left, you've got your concave mirror. It curves inward, kind of like a cave. Its job is to take parallel rays of light and bring them all together. It converges them to a single point. And on the right, we have the convex mirror, which bulges outward. It does the complete opposite. It takes those same parallel rays and spreads them out, or diverges them.
Okay, so to use this toolkit properly, we've got to speak the language. We need to know the names of the parts. So let's define the three most important points you'll find on any spherical mirror: the pole, the center of curvature, and the focus.
First up is the pole, which we label with a P. The easiest way to think about this is as the origin on a map, like point 0, 0. It's the exact geometric center of the shiny reflecting surface, and it's our #1 reference point. Everything we measure is going to be from the spot.
Next, we've got the center of curvature, or C. Just picture that this mirror is a small piece that was sliced off of a giant, perfectly round ball. Well, C is the center of that imaginary ball. It basically tells us how much the mirror curves. And that straight line that connects the pole P and this center C, that's a really important line we call the principal axis.
And finally, we get to the principal focus, F. Now this is where the magic really happens. For a concave mirror, this is a real physical spot where parallel light rays actually meet up. But for a convex mirror, the light rays just look like they're coming from this point. It's a virtual focus that's actually behind the mirror.
So we have our basic parts. Awesome. But to make them work together in equations, we need a universal rulebook, an instruction manual that everyone agrees on. This is called the Cartesian sign convention, and it's the secret sauce that lets one single formula work for every mirror in every possible situation.
You know, the core idea is actually pretty simple. We're just going to treat the mirror like it's on a graph. The principal axis, that's our x-axis. And the pole, P, that's our origin, 0, 0. And here's the most important rule of all. We always assume that light travels from left to right. That's our starting point for everything.
This table right here lays out our 4 golden rules. First, any distance you measure in the same direction as the incoming light is positive. Second, any distance measured against the incoming light is negative. Third, any height measured up from the axis is positive. And you guessed it, fourth, any height measured down is negative. This convention is the absolute key to making sure our math works out. Let's try to apply that right away. Remember, we always measure from the pole, P. So if our object is to the left and the light is traveling to the right, we have to measure from P backwards to get to the object. We're going against the light, and what does our rule say? That means the object distance, U, is going to be negative. This is a super crucial point to remember. Okay, with those rules in our back pocket, we can now find a really powerful and simple relationship that's just hiding in the mirror's geometry. Let's add the next tool to our kit. So, if we look at the geometry of a light ray that hits the mirror really close to the center, these are called paraxial rays, we can find a direct link. We don't need to get into the weeds with the trigonometry, but it reveals a very clean, very simple connection between the mirror's radius of curvature, r, and its focal length, f. And here's what it all boils down to. The focal length, f, is simply half of the radius of curvature, r. That's it. This little formula is a cornerstone for pretty much everything else we're going to do. All right, it is time for the main event. We have the parts, we've got the rules, we have a key relationship. Now let's assemble the ultimate power tool in our entire kit, the mirror equation. This is what connects everything together. To figure out this equation, we use a ray diagram just like this one. See, we have an object, which we call AB, and by carefully tracing a couple of special light rays coming from it, we can find out exactly where its image, A', B', is going to form. This diagram holds all the geometric secrets we need.
Now, we're not going to get bogged down in all the algebra, but the logic here is just beautiful. It all comes down to finding pairs of similar triangles in the diagram. Once we have them, we can set up ratios of their sides, compare those ratios, and that gives us an equation linking all the distances. The final crucial step is to apply our Cartesian sign convention, which makes the whole thing work for any situation.
And here it is, the mirror equation. It says 1 over v plus 1 over u equals 1 over f. Simple as that. Here, u is the distance from the mirror to the object, v is the distance from the mirror to the image, and f is the focal length. This is the power tool that ties it all together.
But wait, that equation only tells us where the image is. What about how big it is, or whether it's upside down? For that, we need one last tool, linear magnification, m. It's just the ratio of the image's height to the object's height, but it's also equal to negative v divided by u. If m turns out to be negative, the image is inverted. If it's positive, the image is upright. And the number itself tells you if the image is bigger or smaller.
Okay, we have officially built our toolkit. Now, theory is great and all, but it's time to get our hands dirty. Let's put these formulas and our sign convention to the test and solve a real problem. Here's our challenge. We have an object. We place it 10 centimeters in front of a concave mirror. We also know that the mirror has a radius of curvature of 15 centimeters. The mission: find the image's location, figure out its nature, is it real or virtual, and calculate its magnification. Okay, the first and most critical step before you even think about an equation is to list what we know and apply our sign convention. The object distance u is negative 10 centimeters because it's to the left of the mirror. Now for a concave mirror, the center C is also on the left, so the radius r is negative 15 centimeters. And that means our focal length f, which is just r divided by 2, comes out to negative 7.5 centimeters. Seriously, getting the signs right is everything.
Now for the easy part. We take these values and plug them into our mirror equation. So 1 over v plus 1 over negative 10 equals 1 over negative 7.5. We do a little bit of algebra to solve for v, and we get our answer. The image distance v is negative 30 centimeters. So what do these numbers actually tell us? Well, that negative sign on v means the image is on the left side of the mirror. It's a real image. Now for magnification, m equals negative v over u, which gives us negative 3. The negative sign there confirms the image is inverted, or upside down. And the number 3 tells us it's 3 times bigger than the original object. See, the numbers tell the whole story. And just like that, we've done it. We've gone from the basic definitions all the way to solving a complete problem. So let's do a quick final review of the powerful tools we've put together in our Physicist's Toolkit today. Here they are, the 3 essential formulas you need to remember. First, the simple link between focal length and radius of curvature. F equals r over 2. Second, our workhorse, the mirror equation. 1 over v plus 1 over u equals 1 over f. And third, the magnification formula. M equals negative v over u. With these 3 and your sign convention, you can solve any spherical mirror problem that comes your way. So, you've now cracked the code for a single curved mirror. You've got the tools. But the real world of optics is full of systems that are way more complex. So a question to leave you with is this. What happens when you take the light reflecting from a mirror and then you pass it through a lens? How do these different toolkits combine? That's where the fun really begins. Thanks for joining me.